In this video, we'll look at an example of how to use a best fit line, how to find the equation of the best fit line, and how to use it to make predictions. So here's the situation. We want to predict the listing price of a house in thousands of dollars based on the house's size in square feet. Right there in that first sentence, you see the word predict. The variable that comes after that has to be your y variable or your response variable. The response variable is the one you're trying to predict. Since we're trying to predict the listing price has to be our y variable, our response. The other variable, house size, would be our explanatory variable. Okay, so whatever variable you're trying to predict is going to be the response variable. Now we have some data here that we gathered from a local real estate website, and we have some houses, and the mean size of the houses that we looked at was 2,053.1429 square feet, and the mean listing price was $220,149, and standard deviation of the house sizes was 600.5929 square feet, and the standard deviation of the listing prices was $43.2039. The correlation between our x values and our y values is 0.8357. Now, if we want to find the equation of the best fit line, what we have to do is basically use our formula for B and our formula for A. We'll plug in the appropriate numbers in the appropriate places, and then we'll see what we get. So let's start with B. You always have to start with B because you can't calculate A until you have B. So you always start with B. Now the formula for B is R times SY over SX. So we're going to plug in 0.8357 for R, 43.2039 for our standard deviation of Y, and then we're going to divide by 600.5929, which is our standard deviation of X. And when we simplify all that down, we get 0.06012 is our value for the slope. And we'll interpret that in a minute. To find A, you use the formula y bar minus b x bar. Y bar is 220.1429. B is 0.06012. And x bar is 2,053.1429. And when we simplify all that down, we get approximately 96.7079. So now we have a slope, we have a y-intercept, and we can write the equation of our line. Price is the response variable. Put a hat on it. Don't write just y here or even y hat. You want to use a more descriptive name for the variable here. Since it's listing price, price would be sufficient for that. Put a hat on it because this is predicted value of price or predicted relationship between size and price. So always put a hat on your response variable here. And here's A, 96.7079, and here's B, 0.06012 times size. Now, you might ask, why do we put the y-intercept first and the slope second? Normally, we look at equations of lines in the form y equals mx plus b, and we put the slope and then the explanatory variable plus the y-intercept. And so it would be in a reverse order from this. Well, when you're working with best fit lines, this is the traditional way to do it, and there's a good reason that you might not understand until later on, but we always put the intercept first, and then we put the explanatory variable with it, with the slope coefficient next. And the reason why is if we were to add more explanatory variables into our analysis, we could just tack them onto the end of this equation right here, and that'd be a lot easier than trying to shoehorn more variables in on the left. It's much easier to add them onto the right. So that's basically why we do it this way. So here's your best fit line. Price hat is approximately 96.7079 plus 0.06012 times size. Now what do these numbers mean? Well, if we're interpreting the slope basically tells you how much predicted price is going to change in response to a unit increase in size. So the interpretation of the slope would look like this. On average, predicted listing price increases by $0.06012,000, which in straight dollar terms is $60.12 for each additional square foot of house size. Anytime you're interpreting a slope, always remember it's an average relationship between the predicted values of your y variable and the actual values of your x variable. Okay, so you always want to have these words in there, and then you want to say if the predicted response is increasing or decreasing, and by how much for each additional square foot of your x variable, or each additional unit of your x variable, I should say. Now, to interpret the y-intercept, the y-intercept is the value of predicted response when your explanatory variable takes a value of 0. So in this situation, for a house with a size of 0 square feet, the predicted listing price is $96.7079,000. Now you might say that doesn't make any sense at all. A house with a size of 0 square feet would not be a house at all. And you would certainly be right about that. This number doesn't necessarily have a lot of intrinsic meaning, but for any line you need to know two things. You need to know where it would hit the y-axis, if it ever does, and then what slope would it have. And with those two things you can completely specify the line. So we need a value for a y-intercept, even if the value of the y-intercept in itself is not very meaningful otherwise. Okay, now we can make predictions. To predict to the nearest $100 the listing price of a house that is 1,900 square feet in size, we just plug 1,900 square feet into our best fit line. So our price hat is approximately 96.7079 plus 0.06012 times 1,900, and that works out to the nearest $100 to be $210,900. So that's how you can make a prediction with the best fit line, and you can make predictions for any value of house size. Any value you want to plug in here, you can make a prediction. You got to be careful though, when you're using values for your x variable, your explanatory variable, to plug in here, you don't want to use values that are very far away from the actual values that you have in your data set. Why? Well, because it's risky. The relationship might break down when you get outside of the particular set of x values that you used. So that's what they call extrapolation. It's kind of risky, trying to make an estimate for your response based on a value of x that is not close to the data values that you actually used to estimate the line. So that's risky, and I don't recommend it. But we just made a prediction for a value of x that is in our data set. We actually have a house in our data set that had 1,900 square feet, and that actual house had an observed listing price of $225,000. We can calculate and interpret this house's residual based on that information. The residual is observed y minus predicted y hat. The observed listing price was $225,000. The predicted listing price was $210,900. The difference is our residual. It's $14,100. If anybody asks you what this number means, you say, well, this house listed for $14,100 more than the least squares regression line predicted. And that's pretty much all a residual is. It's just the difference between what we observe and what we expected to see based on the line. And a positive residual means that the observed value is greater than the predicted value, and a negative residual means the opposite. The observed value will be less than the predicted value. Those are the kinds of things that you typically be asked to do with the best fit line, to make predictions, calculate residuals, and see how accurate your predictions might be. In this case, we underestimated the listing price by $14,100 using our line. In future videos, we'll look at other aspects of best fit lines that are worth considering.